Okay, section 4.5, concentration of solutions. So we're going to get back into calculations now, and we're going to build upon the calculations that we worked on in chapter 3. And so the idea here is essentially this. Imagine that we dissolve some amount of, let's say, salt, table salt. So we measure out some solid table salt. And then we have a coffee cup. So here's our coffee cup. And in that coffee cup, we've got water. Okay, there's water in there. And then we sprinkle some salt in there. Now, salt is sodium chloride, and let's assume that we stir it really well so that it's homogeneous. Salt, table salt anyways, is sodium chloride, right? NaCl. And when you dissolve salt into water, what you get are sodium ions and chloride ions, right? And they're hydrated by water molecules. We talked about that back in sections 1 and 2. Now imagine we sprinkle some more. So we put a little bit more in there and stir it up. And then we sprinkle some more in and we stir it up. What you'll notice is that as we put more and more of the salt and dissolve more and more of it into the water, the amount in the water is increasing, right? So one way to phrase this would be to say that the concentration of the salt in the water, right, is the amount of the salt that dissolved, so amount of dissolved salt, divided by the amount of the solution. So in other words, if we have only a tiny bit of salt dissolved, right? It's very dilute. We would say that this solution has a very low concentration of salt, right? It's a low concentration. On the other hand, up above, there's a lot of salt dissolved in there, so that has a high concentration of salt. Okay? So this is the idea of concentration. It's essentially analogous to density. It's the amount of something divided by the space that it occupies. Okay? So concentration. Now we're going to be a little more quantitative about this. And the way we'll do that is we will introduce a very specific type of concentration unit, and that is called molarity. Molarity, interesting word. The word, in a sense, is related to density. Remember, density is the mass of a substance divided by the volume that it occupies. Molarity is actually just the number of moles of a substance divided by the volume that it occupies. Density is frequently used to describe pure substances or solid materials or liquid materials. Molarity is generally used to describe the case where you have a solute which is dissolved into a solution. Okay, so it's moles over volume. So let me show you what I mean by that. Again, imagine we have this container, and in this container we put 1 liter of water. Okay, you've all seen a 1 liter bottle. They're very popular, right? Or 1 liter solution of Gatorade or something like that. A liter is a very convenient volume. And just so that you recognize this, a few little things about numbers. 1 liter, L for liter, is 1,000 milliliters. 1,000 milliliters is the same as a liter. You may or may not be aware of this, but a milliliter, which is a pretty small volume, right? A milliliter is, well, let's think about it this way. If you have a 1 liter bottle, the little cap at the top, that probably fits around 2 or 3 milliliters. So it's a pretty small volume, 1 milliliter. A milliliter is the same thing as a centimeter cubed. Okay? So if you had a cube which was a centimeter by a centimeter by a centimeter, so a centimeter across, a centimeter in depth, and then a centimeter high, that would be a centimeter cubed. The amount of space that that has is a centimeter cubed. That's the same thing as a milliliter. And those of you that are in the medical field or moving into the medical field, you recognize that a centimeter cubed is the same thing as a cubic centimeter, or a cc. So 1 cc if you're measuring out volumes. Okay? So imagine that this is 1 liter. Now that's pretty big for a coffee cup, but they make them that big. So you have a liter of water in there, and then we put in 1 mole of a solute. So it could be sugar, for example. I could put in a mole of sugar, sucrose. And if I put in 1 mole of sugar, which is the solute, and I divide that into 1 liter of water, which is the solvent, essentially what would happen is the volume when you add the sugar will only change a tiny, tiny bit. Let's assume that it doesn't change at all. It would change a tiny bit, but very little. So if the volume doesn't change, then this would be 1 mole of sugar over 1 liter of solution. And that would be called 1 molar. A molar is a concentration unit where you have 1 mole of solute divided per liter. So 1 mole in 1 liter is a molar. Okay? All right. The abbreviation for molar is a capital M. So we would write 1 capital M for 1 molar. So that's the type of concentration unit that we're going to use. Now I am going to point out here that there are many other units of concentration used. So we're going to talk about molarity, but there are others. There's something called molality. So let me put it in here. Molarity is moles of solute per liter of solution. There's another type of concentration called molality. There's only 1 letter difference, and that's moles of solute divided by kilograms of solvent. So if I have a kilogram of water, water is the solvent, the mass in kilograms would be, that ratio would give you the molality. There's also something called mass percent. And so the mass percent is the mass of the solute. Doesn't really matter what the units are in, but that would be divided by the mass of solution. So this could be in grams over grams, and then you multiply it by 100 to convert it to a percentage. So those are 3 concentration units that are commonly used by chemists and also by biologists. But we're going to focus on molarity in this particular chapter. Okay? So let's take a look at a quick little problem. Of course, you're going to try the practice problems to really go into these, but I want to show you one quick little problem here. And that would be, suppose that we said we're going to dissolve 5 grams of glucose, and glucose has the chemical formula C6H12O6, into 250 milliliters of solution, meaning the total volume is 1/4 of a liter. and we want to calculate the molarity of the sucrose. Molarity of the sucrose solution. Okay, I don't know how sweet that would be, but that would be some sweet water because you got glucose dissolved in the water. Okay, so here's how you go about it. We need to know the number of moles of the solute. The solute is the substance you're dissolving into the solvent. So that would be the glucose. The sugar is what's getting dissolved. And then we would need to know the number of liters of solution. And that would give you the molarity. Okay? So how do we find the moles of glucose if we only have the mass? We have 5 grams of glucose, C6H12O6. What you do is you divide it by the molar mass. Do you remember that from chapter 3? If you have the mass of a compound or the mass of an element, you divide it by the molar mass, and that'll give you the number of moles of that substance. So the molar mass of glucose, you can check this on your own, but it's 180.18 grams. So 1 mole of glucose weighs 180.18 grams. And again, notice we're going back to using this idea of dimensional analysis to get the units right. Grams divided by grams, and that gives us the moles of the glucose. Okay, we want to practice those problems continuously throughout this course. So 5 divided by 180.18, and you get, oops, sorry about this, I've got a little calculator here. 5 divided by 180.18. Okay, well, got a little problem with my calculator here. So let me switch out of this, and let me see if we have a calculator here. 5.00 divided by 180. Oops, sorry, I did 118. So 180.18. Okay, and then I hit equals. So it's 0.02775. So that would be 0.02775 moles of glucose. Okay. Now, we need to divide that by the number of liters of solution, but we don't have liters of solution. We only have milliliters, 250 ml. So this is a conversion you want to practice. 1,000 ml is a liter. This is a really practical type of conversion. You do it a lot in chemistry. Okay, so 250 ml times 1 liter over 1,000 ml. Okay, so the ml cancel, and you get 0.250 liters. So now we're going to divide this by the number of liters, 0.250 liters. Okay, so moles of the solute, which is the glucose, divided by liters of the solution, not milliliters of solution. So again, let's come back over here. And we have this number. We're going to divide that by 0.25. And we get 0.110. So this would be 0.1110. And this would be moles over liter. Check to see if we have too many sig figs. It looks like we do. There's only 3 sig figs in our answer. So 0.111 moles per liter. So that would be the molarity. It's a measure of how many moles of glucose are in a liter of that solution. So if we had 1 liter, we would have 0.111 moles of glucose in that solution. Okay? So that's a little intro there. The next issue that we often deal with is what we call dilutions. This is a very common type of calculation. So let's take a look at dilutions. This is still the same section. Okay, so the idea of dilution is this. Suppose that we have in our container, again, we'll come back to a coffee cup, so you're drinking sugar solution. Suppose we have 0.111 molar glucose. And I'm not going to tell you what the volume of this is. I know we just did a calculation where the volume was 250, but whatever the volume is, it doesn't matter for this type of problem. So we have this solution, and what we're going to do is we're going to say, look, this solution, it's great that it has sugar in it, but it's just too concentrated for us. We want it less concentration. I don't want my kids drinking really sugary drinks or whatever. So here's what you would do. You would say, okay, well, let's take another coffee cup. And let's just take a little bit of this solution that we made here and transfer it over and pour it down to the bottom. And then add water. Right? We've all done this. You add water to it. And what that would do is it would take this solution that's pretty concentrated, 0.11, and now it would be less concentrated. So this is called the dilute solution. The dilute solution is less concentrated. It has less glucose per liter than what is called the stock solution. The stock solution is the solution you're starting off with, which has higher concentration. Okay, higher concentration, lower concentration. That's called dilution. Now, what you can do is you can use this equation. It's called the dilution equation to solve problems. The concentration of the stock, so I'll put S for stock, times the volume of the stock that you take out. So that's this volume that we transferred over. That is equal to the molarity of the dilute solution. So that's this solution in here, times the volume of that dilute solution. That's the total volume of the dilute solution. It's a very nifty little equation. MS Vs equals Md Vd. There are many different forms where different symbols are used. You might see M1 V1 equals M2 V2. That's another way it's shown. Another way is C1 V1 equals C2 V2. Your textbook actually has some different ones. It actually says MS times LS, meaning liters of stock, equals M of the dilute times liters of dilute. So there's many different forms of this, but really what it says is the concentration of the stock times the volume you take out of the stock is going to be equal to the concentration of the dilute times the volume of the dilute. The volume of the dilute is going to be larger than the volume of the stock because you're only taking a little bit of the stock and then diluting it. It's the total volume here, okay? The molarity of the stock should be higher than the molarity of the dilute because you're diluting it, right? You're adding water to the dilute, so it should be less concentrated. So let's do a quick little problem here so you can see this. It's a beautiful way to be able to make predictions about concentration. It's a very practical issue. So again, let's come back. Let's say this is 0.111 molar glucose. And this is our dilute solution. And so what we want to do is we want to say this. This is a typical type of problem. We want to take a volume of stock solution and dilute to 250 ml with a concentration of 0.010 molar. Sorry, that M is kind of funny there, right? I get carried away with my M's. Okay. What volume of stock solution do we need to transfer? In liters and milliliters. Okay, so that we want to answer that in liters and milliliters. Okay, all right. Take a volume of stock solution, dilute it to 250 ml with a concentration of 0.01 molar. That's really a change by about a factor of 10. If it were 0.111, that would be 1/10. But let me show you how we would go about it. What we would do is we come back to our dilution equation, MSVS equals MDVD. Okay? And we want to know what volume of stock solution. So that's VS. We want to know what this is. So how do you find VS? You divide both sides by MS. So you take the molarity of the dilute times the volume of the dilute, and you divide that by the molarity of the stock, right? Divide both sides by M sub S. So do we know the molarity of the dilute solution? It's right here, 0.01 molar. We want to multiply that by the volume of the dilute. It says 250 ml. And then we're going to divide that by the molarity of the stock solution, which is right here, 0.111 molar. Notice what happens to the units. Molarities cancel. Remember, molarity is moles per liter, and you're left with milliliters. So this is going to give us an answer in volume units of milliliters. So 0.01 times 250 is easy. That's 2.5. So 2.5 divided by 0.111. So I'll just do that on the calculator here. So 2.5 divided by 0.111. And it looks like it's 22.52. I'll round it to 22.5. Okay, so what that's telling us is we need to transfer over 22.5 milliliters of stock solution. And then once we've delivered it over here, we add water until the total is 250 ml, and that will give us a concentration of 0.010 molar solution, less concentrated than it originally was. Now, it says in here to do it in liters and milliliters, so let's do it in liters. So the conversion factor, 1,000 ml, not 1,000 liters per milliliter, but 1,000 milliliters per liter. A milliliter is small, so there's a lot of milliliters in a liter. Okay? Milliliter, think of a thimble, if you remember what a thimble is, if you've ever done any sewing. A thimbleful is a milliliter. A liter is a big bottle. So there's a lot of thimbles in 1 liter. So there's our conversion factor. So 22.5 ml, and it's a liter over 1,000 ml. Milliliters cancel, and you get 0.0225 liters. In other words, a small fraction of a liter, right? 22 milliliters divided by 1,000. Okay? There you go. So that's the idea of dilution. Now, there is in this section a discussion of a couple of different things that I'm not going to go in great detail over. One is serial dilutions. Serial dilutions is the idea that what if you need to dilute something by a huge amount, by a factor of 1,000 or 10,000. It ends up being not practical to dilute things by a factor of 1,000. So it's more practical to dilute things by a factor of 10, and then to take that diluted solution and dilute it by another factor of 10. So let's say, for example, I have a stock solution, and it has a concentration of 11 molar. And I want to dilute that to 1 times 10 to the minus 3 molar. That's a huge difference in concentration. And practically speaking, you can't really do that in one dilution. If you do the calculation, you would find that you need such a small volume to take out that it's hard to measure it accurately, and then you'd have to dilute it into a huge volume. So we can't really do that in one dilution. So what we would do is we would take our 11 molar, take some of that out, and dilute it to, say, 1.1 molar. That's a factor of 10, right? 1.1 is a tenth of 11. So we would do a dilution to get it down to that value. And then we might do a second dilution by a factor of 10, and that would get us to 0.11 molar. So this is dilution number 2. This is dilution number 1. And then we do it again, 1 over 10. So like take 10 ml out and dilute it to 100 ml. That'd be a factor of 10. And then so now you got 0.011 molar. And then, so that's the third dilution. And then you could do a fourth dilution by a factor of 10 and get it to 0.0011 molar, which is 1.1 times 10 to the minus 3 molar. So 4 dilutions by a factor of 10 will get that to you. So that's called serial dilutions. Okay, so that's discussed in your textbook as well. In fact, there's a nice picture on figure 4.12 where it shows you going from high concentration to low concentration and how the color of the solutions become less and less dark. Okay, so the next one, the next issue that comes up in this section, sort of the final for this section, is the idea of what they call solution stoichiometry. And this is the idea that sometimes, compounds, ionic compounds in particular, when they dissolve into water, they form multiple ions, right? So for example, this is sodium sulfate. Sodium sulfate, if you dissolve it into water, will form 2 sodium ions and a sulfate ion, right? Sodium sulfate, right? But notice the stoichiometry. Every time one of these is dissolved, you get 2 of those, and you get 1 of those, right? So you actually get 3 particles here for every one of these that you dissolve. That's generally not true for molecular compounds, except for maybe acids. Molecular compounds, they dissolve, but they're hydrated, but they don't ionize, they don't break up into smaller particles. So suppose I said the following. I'm going to put 1 mole of sodium sulfate into a liter of solution. What would be the molarity of the sodium sulfate? Well, it's a little tricky because it turns out there's a couple of answers here. One answer is there's a concentration of sodium, and then the other answer is there's a concentration of sulfate. So what we could say is, look, the concentration of sodium, and I'm going to use something called bracket notation. You will see this quite a bit in chemistry. When you see these square brackets around a symbol or around a chemical formula, that means concentration of, right? Concentration of. So the square bracket means concentration of in this context. So the concentration of sodium ions would be the following. There's 1 mole of sodium sulfate, but there's twice as much sodium. So it would be 2 moles of sodium for every liter of solution. So that would be 2 molar. So the concentration of sodium ions is actually 2 molar, not 1, even though you put 1 mole of sodium sulfate in. What about the sulfate? Well, the concentration of sulfate, stoichiometrically, right, there's the concentration of, well, every time one of these dissolves, one of the sodium sulfates dissolves, you get 1 sulfate. So that would be 1 mole of sulfate per liter. And so that would be 1 molar. So what you get is a result in which 1 part of the compound, the sodium, actually has twice the concentration of the other part of the compound, which is the sulfate. So 1 molar sodium sulfate actually produces 2 molar sodium and 1 molar sulfate. So that's the issue of solution stoichiometry. Okay? Now, there is one more topic in here that's discussed, which is called spectrophotometry. And that is on page 163. And I'm going to discuss this very briefly. And the idea here of spectrophotometry is that it is a method, spectrophotometry. This is a method that's used to measure concentration, a way to measure it. Molarity. It's used a lot in the medical field. Laboratory technologists in the medical field, clinical technologists, they measure concentrations of solutes in urine, in blood, in plasma, in fluids quite frequently. That's one of the things that they're really good at doing. And spectrophotometry is a method where we use light. Spectro meaning we're using the spectrum of light. Okay, photo means light. This is measuring. So we're measuring the spectrum of light when we use spectrophotometry. And it's based on the following idea. I'm going to be very kind of crude about this. Imagine you have a light bulb, and the light bulb is producing light. Okay, it's shining light outward. Okay, if you take some of the light and you kind of filter it out in a way so that only light that's moving in a straight line here is coming through. And then what you do is you put something called a prism in front of it. The prism can actually split the light into different colors. Okay, so here's our light source. Splits it into different colors. So you might have red light over here, you might have green light over here, and you might have blue. So if you pick one color, so let's take the green. And then you take a special little container called a cuvette. It's called a cuvette. And you put your solution in there. So you have these little particles in there. So it could be like food coloring or something like that. In water, so it's in a solution. What you can do is you can measure how much light is coming in and how much light is coming out. And if you take a ratio, the amount of light going in divided by the amount of light going out, the amount of light going in should be at least equal to the amount going out, but it might be less. I'm sorry, it must be the other way. The amount of light coming out might be less than the amount of light going in. If it's less coming out, that means that whatever is in there absorbs some of the light. We call that process absorption, absorption of light. Okay? So it turns out if you take that ratio, the amount of light coming in divided by the amount of light going out, and then you take the logarithm of it, base 10, you get a quantity called absorbance. Okay? And you can plot this absorbance, A for absorbance, ABS, versus concentration. Okay, so this is increasing concentration. So low concentration, 0 in fact, over here on the y-axis, and then higher concentration out here to the right. And it turns out that if you start changing the concentration and making it higher and higher and higher, the absorbance increases in a linear fashion. It's a straight line relationship. Okay, now I can't draw a real, well actually there might be a little tool here. I'm not going to look for it to draw a straight line. It's what we call linear. meaning it's very predictable. If I double the concentration, we double the absorbance. So in practice, what you do is you make several solutions of known concentrations. So one where there's just water, so the concentration of the solute is 0. Another concentration where it's higher. Another concentration where it's higher. Another concentration where it's higher. And you measure this ratio, the log of the amount of light coming in divided by the amount of light coming out, or absorbance. And then you make a graph of that. What's the absorbance versus concentration? Then you take an unknown sample, something that you don't know its concentration. And let's say that you measure its absorbance and it's right here. Well, if you read over to this line and then read down to the x-axis, that tells you the concentration. The absorbance is related to a particular concentration on this line. So this relationship, this linear relationship, is called the law of beer, not beer as in the drink, but it's named after a person, of Beer-Lambert. And it's the law of absorption. What it says is the absorbance of something that's absorbing light increases in a linear fashion with the increase in concentration of that substance. So the more concentrated it is in here, the higher the absorbance is going to be. Okay? So that's a very powerful tool used in chemistry, used in biology. For those of you who are biology majors, at some point you'll probably do some sort of enzyme reaction where you measure the change or the disappearance of color of something in there in the solution, and that's spectrophotometry that you're using. It's also used in the medical field quite a bit. Okay? So one point, section 4.6, aqueous reactions and chemical analysis, you are not responsible for section 4.6. So let me make a little, I'm just going to write this in here. Section 4.6, which is aqueous reactions and chemical analysis. Not responsible for that. Okay? All right, there you go. So there's section 4.5. You definitely want to practice as many of the practice problems as you can for this section, and good luck.